Welcome to another exciting, okay, no, maybe not, it's not exciting. Welcome to another amazing, all right, maybe it's not amazing. Welcome to hopefully an enlightening lesson by Mr. Rast, Thanksgiving special. I'm Mr. Rast, and this is my Thanksgiving special on topic 5, the periodic table. Let's talk about the history of the periodic table and the composition of it right here. So in 1865, John Newlands arranged the first 16 elements, excluding hydrogen and helium, in order of increasing atomic mass. So he takes the first 16 elements, really it's starting with number 3, lithium, and he puts them in order of increasing atomic mass. So you have lithium is the lightest and argon would be the heaviest. He found that elements in the same column had similar chemical and physical properties. Because properties repeated with the 8th element, he called this pattern the law of octaves. So John Newlands is credited, what I think you should note most, is that he's credited for writing the law of octaves. And what that means is then after 8 elements, lithium, barium, boron, carbon, nitrogen, oxygen, fluorine, neon, he found that after 8, the 9th element started to repeat properties. So lithium and sodium have chemical and physical properties very much like each other, where barium and magnesium also have properties very much like each other, all the way over to neon and argon, fluorine, chlorine. And so because these properties repeated, now they're obviously different elements, but they're very much seem to be somewhat related to each other as far as chemical and physical properties are concerned. So that was John Newlands, and he would be the first person to arrange elements and kind of figure out a pattern in them. However, it was Dmitri Mendeleev that really put everything all together and would be credited with writing the first periodic table. So he developed and arranged all 63 elements that were known in 1870, and he arranged them by atomic mass. So he's got all the elements that are known at the time, and he arranged them by atomic mass. And he put them in groups so that these groups would, like what Newlands did, these groups would have similar chemical and physical properties with each other. Okay, so things to note. The elements did not fit neatly in order of increasing atomic mass. And you might say, all right, well, it looks like it. You have tin and tellurium, and this J actually would be, I guess, was the old symbol for iodine. I don't remember where I got this picture from. But anyways, this J would be iodine. So it looks like it's working 122, 25, 127, so it's increasing. But Mendeleev had to reverse the order of tellurium and iodine to keep similar elements in the same column. So in other words, tellurium he knew had properties that should belong in the column with oxygen and sulfur. He knew it should belong in this column, and he knew iodine should belong in the column that had bromine and chlorine and fluorine in it. And so he reversed the order, but the numbers don't look reversed. And what I'd like to kind of point out here is if we take a look at a periodic table, and we look here at tellurium and iodine, the elements in question, his table was in order of atomic mass. And today we know that the atomic mass of tellurium, 127.9, is actually heavier than the next element of iodine, 126.9. It's very unusual in that kind of pattern, but tellurium is heavier than iodine. And even though it's heavier than iodine, it seems to me that Mendeleev ignored that and perhaps said no, tellurium is lighter because it should go here. He knew it should go there. He understood some pattern of the periodic table, but I don't think he quite understood why it was what it was. And this would be an example of bad data. When we do labs in class, sometimes you know what you're supposed to see. You know what you're supposed to get on something. And maybe you just say, hey, you know what, maybe I took a bad reading, so I'm going to put a reading that would fit what I expect it to be more likely. I'm going to make it fit. And that's what it looks like here with Mendeleev. Tellurium is heavier, but the data is showing that it's lighter because he knows it's supposed to fit here. But he didn't understand something about the elements, everything altogether by the time he made this. We'll talk about that in a moment. In particular, it has to do with this atomic mass. One of the really brilliant things that Mendeleev did is he put gaps. He placed gaps in the table where he was and in these gaps, see these gaps right here, he said there's supposed to be elements here. We just haven't discovered them. But I know, because I understand this pattern, that there's kind of a skip here. There's a space. So there's going to be something in between the mass of these two elements that's going to fit and behave like this group here. So this is quite brilliant. Gaps were placed in his table where he was able to predict the behaviors of yet discovered elements. And so what's really cool about what Mendeleev did, in that brilliance of leaving the gaps and organizing this stuff, when future elements were discovered, take a look at element 101, Mendeleevian. So this element was named after this brilliant scientist that came up with our first periodic table, Mendeleevian. Scientists later credited that element to him. So I think that's pretty darn cool. All right. Later, Henry Moseley designed periodic tables based off of periodic law. The physical and chemical properties of elements are periodic functions of their atomic number, not the atomic mass, the atomic number, which is the amount of protons. This was discovered again by Henry Moseley. This is the model for periodic tables we use today. They are ordered by atomic number. So when we look over back at that periodic table I was showing you guys, these numbers, this is not, see, tellurium is 127 and iodine's 126. It is not in order of atomic mass, but in order of atomic number. Tellurium has 52 protons, where iodine has 53. So it's order of atomic number, the amount of protons, not the average atomic mass. So that little fix to the brilliant idea that Mendeleev had was done by Henry Moseley, and it's called the periodic law, and it's how we have our periodic table organized today. Okay, in the periodic table, elements that belong to groups 1, 2, 13 and through 18, which is the S and P blocks, these are called main group elements. Main group elements. So 1, 2, 13 to 18. Let's take a look at that real quick. 1 and 2, that's the S block. And if you're not familiar with what I'm talking about, the S block, please go back into the last topic, topic 4, and review that. So the S block right here, that's group 1 and group 2, and then it said group 13 through 18, correct? Group 13 through 18, which is the P block. These are main group elements. So let's take a look over here. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So 13 to 18 is the P block. So 1 and 2 S block, 13 to 18 P block. So let's take a look back now at what this says. Elements that belong in groups 1 and 2 and 13 to 18, S and P block, are main group elements. They have very regular electron configurations. They're very consistent. Their patterns, their behaviors are very consistent. Let's put it that way. And we'll get into a lot more detail on that in this class. So they have very regular electron configurations. Sometimes main group elements are referred to as representative elements. So be aware, I may use these two words interchangeably, and you may read about these elements interchangeably, you know, if you're reading about it online or in textbook or whatnot. So sometimes called the representative elements because their behaviors, is so constant. So S and P block, very constant behaviors. All right. Okay, so let's talk some vocabulary with the periodic table. Firstly, periods are horizontal rows of elements on the periodic table. So horizontal means going this direction, horizontal. So periods are horizontal rows, the rows on the periodic table. So this is a period going across here. This is a period, okay? The next term I will use is group. So if I say period, I'm talking about rows. I will probably stop saying rows in the near future. When we're talking in class, I will say what period it's on. And if I say group, I'm talking about columns. Columns go vertically up and down. So a group, or sometimes referred to as a family, is a vertical column of elements in the periodic table. These groups or families, if you've noticed before with what Newlands did and Mendeleev did, is they grouped things together vertically. And because they behave a lot alike, they're like family, because you have a lot of characteristics like the people in your family. Okay, the next term is metals. Metals, these are elements that are good conductors of heat and electricity. So when we talk about the metals on the periodic table, they are located, if you notice a lot of periodic tables, they have this like little stair step line here, and your metals are located to the left of that line. So the elements to the left, which would include our little F block over here, all of these guys here would be our metals, okay? Metals, it's fun to say. So they are good conductors of heat and electricity. The nonmetals are usually poor conductors of heat and electricity, and they would be located to the right of that stair step line. So these would be your nonmetals over here and your metals over here. Metals would be to the left of the stairs, nonmetals to the right of the stairs. So when you see periodic tables with the stairs, that's what it means. That's why it's there. Now, semiconductors, or often referred to as metalloids, are intermediate conductors of heat and electricity. There are 6 elements located on the stair step line. So these are the 6 elements located on the stair step line. So these are intermediate conductors of heat and electricity, and we call them semiconductors or metalloids. And they are located on the stair step line. I wouldn't necessarily memorize these elements. I would use your periodic table to identify those elements. So your elements are on that line. So your semiconductors are boron, silicon, germanium, arsenic, antimony, and tellurium. So these guys here are our semiconductors. Everything over here would be the metals. Everything over here would be the nonmetals. These are our semiconductors, are often referred to as metalloids. And the words are disappearing. Peaceful. All right. So the next thing is, when we talk about heat and electricity, I'd like to kind of describe the concepts of transferring heat and electricity. And a very easy concept to understand, or that's usually introduced, is the free electron model. A model of, and this is a model of metallic solids where the locations of the nuclei are fixed, but by their lattice sites, but the valence electrons are delocalized through the hole. So electrical conductivity requires an electron to be able to move. So the free electron model says basically here's the nuclei. So when you know if there's a metal, it's not moving around like a liquid. So the nucleus is fixed, but the electrons are free to move around. So if the electrons are free to move around, you can conduct electricity through it. This is why metals conduct electricity. And in this model, nonmetals would have the electrons fixed around the nuclei, and that's why nonmetals cannot conduct electricity, because those electrons are not free to move around. They're around the nucleus, where in a metal, it's like a sea of electrons. It's a very simplistic model that's used, and it's pretty good, but we're going to go a little bit further in our understanding of this, and it doesn't quite explain how semiconductors work. If a metal, the electrons are not localized, in a non-metal, they are localized, then how can this model explain semiconductors? To do so, we're going to get a little more detail here on the chemical properties of elements, and we're going to talk about the band structure model. A model of electric structure of metallic solids in terms of molecular orbitals, in which the electrons may spread over several atoms or the entire metallic solid. So that definition is kind of a textbook definition, so let me try to break it down and make it sense to you. So if we take a look at the band structure model, and we're filling up, and again, if you're not sure what I'm doing right here, this is going back to are, if you don't know what this 2s is, you need to go back to the last topic, topic 4, and take a look at this stuff. So the valence electron in lithium is, there's one valence electron in lithium, and it's the 2s. And I can briefly explain this, try to quickly, but if this isn't enough, please go back. So lithium right here, it's got 3 electrons, and it's got the first column, that's the first shell, has 2 electrons in it. It's got the 1 and the 2 electrons and the 1s, and now we're at the second one, 2s, and we've got 1 electron in there. So that it's got 1 valence electron in the second row in the s block. So that's why I have this here. So in the band structure model, if you've got a group of lithium, if you got a group of them, another lithium is going to add another valence electron, but also another orbital. So you have this spot here. And the idea is, with the band structure model, if electrons are free to move, they can conduct electricity. So they're not locked up here. They're free to move, and they can conduct electricity because there's basically room in here. They can kind of move back and forth into these available spots. So if we had 4 lithium, we would have 4 valence electrons, but we would also have 4 orbitals available. So this is illustrated with a band, and in this situation you can see that the band has this colored area would represent the electrons, and you have this open area which would represent open spots for the orbital. Because if you added some energy here, or these electrons would have a place to move, because they'd have a place to move, this would mean that the electrons, that the material can conduct electricity because the electrons have space to move. If they were rigid and locked in place, they couldn't conduct electricity. So the empty space allows electron movement, hence electron conductivity. Note that the 2p orbitals are not needed here, so just the fact that it's got the 2s is enough. Now, beryllium is element 4, so it's got 2 electrons in the core and it's got 2 electrons in the valence. And in this situation here, we have on the same shell, we have the 2s and the 2p. And what we have here is what we call overlapping bands. So that's very little energy is required to move electrons in partially filled bands or overlapping bands. So the energy jump from 2s to 2p is not very high. In fact, the bands overlap a little bit, so these electrons can kind of bounce back and forth here quite easily, giving room in here for these guys to move and room in here for these electrons to move. Does that make sense? So because of this idea that the energy level from the 2s to the 2p, it actually overlaps a little bit, we have what we call overlapping bands, giving a little bit of room here and a lot of room over here. But regardless, since the electrons are not locked in place, they can conduct electricity. So let's explain how semiconductors come into this. What happens here is with the band structure model is, if we take a look at silicon, they would represent a band that's full of electrons, and then you have an empty spot where the electrons could move. They could move, but there's an energy gap here. The bands are not overlapping, and this energy gap is called the forbidden gap. It sounds terrifying, the forbidden gap. Maybe it could be a movie or something like that. The forbidden gap. So the electrons here cannot move. There's no empty space, and here there are no electrons, so there's no movement, and in between them we have this forbidden gap. A greater amount of energy is required to get an electron to jump the forbidden gap. So if you add enough electricity, one of these electrons, or several, but if one of them will jump the forbidden gap and make it over here, it can move, and because now there's space here, these guys can move. So how semiconductors work is that they do not conduct electricity unless you give them more energy. So they're a little resistant at first, and when you give them enough energy, it kind of kicks on, and then it conducts energy quite well. And this is a really important thing to note. If given enough energy, anything can conduct energy. If given enough energy, anything can conduct energy. So even non-metals can conduct electricity. You just have to give it enough energy, and it will actually transfer energy around. The larger the gap, the better insulator it is. So the greater the forbidden gap, the better insulator it is. And insulator means it doesn't conduct energy well. So semiconductors just have a small gap. So by the band structure model, what we're saying is that metals have overlaying bands. Semiconductors have a small forbidden gap, and nonmetals have a large forbidden gap. So let's take a look at a trend on the periodic table. As we move down the periodic table, we find that the forbidden gap decreases. So if you take a look at group 14 on your periodic table, which starts at carbon, we're going to take a look at this group here, and we see that carbon is a nonmetal, silicon and germanium are semiconductors, and then tin and lead are metals. So using the band structure model, we would say that carbon is a nonmetal because it's got a large forbidden gap. Silicon is a metalloid or a semiconductor, and it would be represented with a gap that is closer together. Germanium would have even a closer gap, but tin and lead, we'd have overlapping bands, which so these guys conduct electricity very easily. Here we need some energy to kick these guys into being able to conduct electricity. And carbon could, but you'd have to give it a lot of energy to jump that forbidden gap, so it would be allowed to conduct electricity. So elements found lower on the periodic table need less energy to conduct electricity. So lead was the lowest. So the lower you go down, so that this trend, the lower you go down the periodic table, the less energy you need to conduct electricity. So the lower you go on the periodic table, the more things behave like a metal. And that's an important thing. This topic, the periodic table, if you're wondering to test questions and stuff that they're going to pop up, it's a lot to do with the trends of the periodic table. And here is the first trend that you should be making sure that you note. As you move down the periodic table, things behave more and more like metals. All right, so now let's talk about those certain groups on the periodic table, those families, and what makes them special, what makes them what they are. So the first one we're going to talk about is the alkali metals. These are metals that are highly reactive metallic elements, and they're located in group 1. And I mean extremely reactive. So group 1 is right here. We're going to exclude hydrogen from the alkali metals. So we're going to go from lithium down to francium. These are the alkali metals. They are, I don't know if, let's see, couldn't see that very well. So we're going to go from lithium down to francium. These are the alkali metals. And when I mean highly reactive, these guys will react with water. If you put a piece of one of these alkali metals in water, they'll react so violently with water, they actually strip the hydroxide. They split water molecules in half, let's put it that way. They split it in half, and part of it bonds with the metal, and the other part is hydrogen gas. And it happens so quick that the hydrogen gas actually reacts with the oxygen in the atmosphere, and it catches fire. So you put these guys in water, and it makes water catch fire. I would say that's pretty reactive. Your next group is the alkaline earth metals. These are reactive metallic elements as well, but they're located in group 2. They are not as reactive as the alkali metals, but they still will react with water in the same fashion. It just won't be as quick of a reaction, and you're not going to get that kind of fire right on the surface of the water. So elements, alkali earth metals are beryllium down to radium. So these guys here, group 2, are called the alkaline earth metals. Remember again, group 1 is the alkali metals. Group 2 is the alkaline earth metals. Now, the next block, we're going to call all the metals in this next block transition metals. These are metallic metals, and they're found in groups 2 through 12. I'm sorry, 3 through 12. These are the alkaline earth metals. These guys here would be more appropriately referred to as, it's appropriate that the transition metals, but what we're familiar with from the last test is if it's, remember, group 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 3 through 12, this block right here, these elements, and hopefully you are familiar with the fact that what I'm going to say next, that these are the D block elements. The D block elements are transition metals. So the transition metals go to here. And let's talk about another family that's important, another group. And I'm going to go all the way towards the end here to the halogens. I want you to know the halogens. This is group 17. These are highly reactive non-metals. These are gases. And these gases are very, very reactive. They would go from fluorine, chlorine, bromine, iodine, acetine. These guys here are highly reactive gases. Very, very dangerous. In fact, the first form of chemical warfare was that of chlorine gas, just elemental chlorine being used. These guys are very, very hazardous in their elemental form, very dangerous. So that's the halogens. That's group 17, because remember we're at 13, 14, 15, 16, 17. I'm sorry, this is 12. 13, 14, 15, 16, 17, 18. So group 17 is the halogens right here, starting with fluorine. And the final family that I want you to be concerned with for my test is the noble gases. The noble gases are group 18, it's the very last group, and these are unreactive gaseous elements. It's interesting that just one atomic number difference from fluorine to neon, you go from extremely volatile to benign, unreactive. So, or what a good chemistry term is, these guys are inert. And it does include helium. Helium is a noble gas, and it goes right down. And these guys here, very, very stable and rather non-reactive. In fact, they're so non-reactive that if you have reactive material, often we pack it around the noble gases so that they would not react with something else. Okay, so alkali metals, alkaline earth metals, the transition metals, halogens, and noble gases. I want you to be familiar with those terms, where they're located, and a little bit about their properties. So, in review, topic 5, lesson 1. What I'd like you to do is work on this workshop here. I got 4 questions here with subparts to them. And remember at the very bottom there, it says, remember to review all of 5.1 notes, not just these questions. It's not like there's calculations going on here, so you have to be very comfortable, very familiar with the concepts. A lot like the last topic, topic 4, there was a lot of test questions that you have to be familiar with the concepts, and that's going to be the case here with topic 5 as well. So number 1, who was credited for the following things? So and all these answers are available in the notes, so if you go back in the notes, you should be able to find the answers to these. And if you can't figure it out, you don't understand it, please note it and ask me, and I'd be happy to help you out, and we'll move on from there. Have a great Thanksgiving and happy Turkey Day. Bye.